Test. Test. Test, test, test.
La glace, il faudrait...
Test. Ok.
Ah, mais t'en as un, ok.
On est parti? So, okay. So, welcome at the award ceremony of the BAPC and the BXOI. First, thank you for participating in the contest. I hope that you had some fun. Yeah? The plan is to first hear something from Mr. Sanders, which is from IMC, our main sponsor. Then we will do the BXOI Awards. So for those who don't know, that's a contest for the students in secondary school. Okay? And then we will do the presentation of the solution for the BAPC, then the awards for the companies, and then finally the awards for the main contest. Okay? So first thing first, I will call Mr. Sanders for IMC, and it will make some noise because I have to change the microphone.
Okay. Thank you very much. On behalf of IMC, I want to thank you all very much for letting us be the main sponsor. As a company, we have a lot of affinity with algorithms, and we have some serious programming competitors that enjoy these type of competitions. But I think a lot of you probably saw the name IMC and said, who? What? So that's why I was just going to maybe steal 5 minutes of your time to briefly tell you who we are, what we do, and why we could be a really interesting company for anybody to work for that has an interest in mathematics, software development, or a lot of areas affiliated. So we're a proprietary trading firm. That's what we are. And proprietary basically means we trade with our own money for our own risk. We trade financial products on over 100 different exchanges across the world. And we provide liquidity for other parties to trade. And we're regulated as an investment firm. Really briefly, we're a Dutch company. We were founded in 1989. We have about 570 employees across the world and growing. We work with cutting-edge technology. I'll tell you a little more about that later. We have a global presence. We are active in the United States. We have an office in Chicago, from where we trade on America and South America. We have an office in Europe, Amsterdam. We have an office in Australia, from where we trade on Asia. One of the other things that's very important to us at IMC is actually giving back. We do a lot of charity work, and we really try to do something back for society with the profits that we make. But trading, why is trading interesting, and what kind of trading do we do? We are a market maker. Does anybody know what that means? Nobody? Okay, very quickly. A lot of people, when they think of trading, they think of people buying stocks and taking a position, keeping a stock, and selling it a while later for a profit, and actually having an opinion that that stock is going to go up. That's not what IMC does. What we actually do is we offer a service on exchanges, and we always are prepared to trade anything at any time. So rather than say we're going to buy one stock of, you name a company, we're going to say, okay, we have a theoretical idea of what the stock is worth, and we'll offer a price to buy it and to sell it. And usually have a very small split in between where we make a profit. So if we think a stock of Shell is worth $100, we'll buy it for $99.99 and we'll sell it for $101. And in between we'll make exactly 2 cents profit. So how do we make enough money? We have to do millions of trades. How do we make millions of trades and do that successfully? We automate everything that a trader used to do. Basically, we look at the financial product, we have a pricing model, we have a strategy behind it to say, okay, if it gets bought or sell, or if the market moves, this is how we feel the price should be adjusted. We capture that strategy in our trading platform using algorithms, and then we trade automated all day. Our history is we started doing this in 1989 when it was still a lot of guys standing on the floor screaming prices and trading that way. And somewhere in the course of the 90s, somebody noticed that, hey, some backup and some analysis using an Excel sheet is useful, and it grew from there all the way into automated trading where we are today. And we existed for almost 30 years, so we're very successful at doing this. And what's interesting is that it's very technology-driven. We have to get 2 things right. Our trading strategies, obviously, our pricing models, what do the financial markets do, and understanding financial instruments. So there's lots of challenges on the finance side, but also technology. Does anybody know why technology might be important to a trading firm? Long story short, we have to be very fast and obviously good. We can't use any third-party software, so everything we do, we develop ourselves, and everything has to be optimized to milli, micro, and even nanoseconds. And that means that we invest awful lots continuously in better software, better hardware, and better forms of transporting data. So what we believe in is creating fair, reliable, and transparent markets. So what is actually the function of this market maker? Why are we there? We provide liquidity. What does that mean? Well, if your pension fund wants to sell a stock and there's nobody there to trade with, they can't sell it. And they have a risk. They have to hang on to it. If there's a market maker there, you're always able to buy or sell any product, and that way transfer your risk. So that's what we do. Another reason we're there, or actually an added advantage of being in the market, is that prices get much tighter. The more competition there is from market makers, the smaller the spread between the buy and the sell. So in the end, everybody trades for cheaper prices. We're constantly looking for people. I can tell you all sorts of attributes that we're looking for, but important thing is that we're looking for problem solvers that like to have fun, that like to work in an informal environment, that like to be challenged every day, because to some people it might sound like you build a trading bot, you let it run, and that's it, and that's far from reality. Reality is that markets evolve, strategies evolve, technology changes, competitors are always changing, so we're always striving to be better than the day before, and that's who we are as a company. So I think everybody's probably really interested in hearing a whole lot more about IMC, so feel free to drop by the stand and have a chat with me or one of my colleagues. But for now, I just want to thank you all for listening to me and wish you a really great time the rest of the evening and the presentations and the prizes. So have a good day. Crazy here.
So thank you, Mr. Sanders. Now we will begin the BX award ceremony. And so I will lead the floor to, to Marcel Vassois.
Merci bien. Okay, do we have slides? There's a PowerPoint available if everything is okay. Yeah, they're working on it. There it is. Okay. Well, this is the first time the BXOI is organized. And I think we had a terrific BXOI for the first time. On behalf of the organization of the BXOI, I want to thank you, the organization of the BAPC, and of course the sponsors who were willingly to give us some goodies. Of course, the opportunity to perform right here, and for the nice t-shirts. The t-shirts, yeah, you can say about it, if you have an Olympiad with no t-shirt, you don't have an Olympiad, right? Well, the contestants had 5 tasks to solve, and after 4 minutes we discovered a mistake in our test data, and I think that was the fastest discovery of a mistake in the test data. That was amazing. Okay, in the next slide you can see the final scoreboard. Oh, I can do that myself, sorry. I don't know where to press actually. There. Oh, sorry. Doesn't matter. Here you see the 16 participants, and they all scored some points. That's clear. And well, here you can see who the winners are. And I think there are no losers because this was just a matter of practicing and picking up a lot of experience. Yeah, the first 3 assignments were easier than the last 2, but yeah, I think we have a nice distribution over the scores, and we have a clear ranking. Okay, I would like to ask Bruno Ploemhans to come down, Jean-Marie Jans, and Ludovic Galland for the awards. Bruno, he is from the Belgium delegation, and I would like to ask him to overhand the bronze medals, and for that we need this slide. So can Siebrand, Jerome, Jan and Maurits come down here for their medal. Yeah, those are the 4. Maurits, where are you? Final picture. Yeah, we need all 4 of them on the picture. Okay. Okay, and then we go to the silver medals, Sebastian and Jan Kwan. Yeah.
It's the goal.
It's a gold?
You
Oh, I made a mistake there. Is that so?
yeah. Jan Kwan, it's gold. And also Sebastian, it's gold.
Oh, I mixed up the two slides.
It's okay.
It's okay now? Oh, fantastic. ZG and Tom. Then. Yeah. And the ceremony will be done by Ludovic Galland. Yeah, and the gold winners, it's clear that's Sebastian and Jan. No? Yeah. And the ceremony will be done by Ludovic Galland. Oh. Yeah. Oh, Jean-Marie.
Anyway.
Oh, anyway. I made a mistake there. Okay, thank you very much. I hope that the next BXOI can be organized together with the next BAPC. That would be terrific. Thank you very much.
So that was it for the BXOI. Next is the main contest, the BAPC. Yeah? Woo! But first thing first, and mainly for our viewers on YouTube, so we are live. We will do the presentation of the solution, and so I leave the floor to the jury. Please applaud them.
Thanks, guys. So we've worked hard on these problems for the last couple of months, and we're really happy to see what you've done with them. So we're going to walk through the problems roughly in order of difficulty. And the first one was a game no one can win. We had a small bet, actually, that this problem would be solved, I said, after 5 minutes without any wrong answers. I turned out to be wrong, although calculating actually submitted something after exactly 5 minutes, but it turned out to be wrong, which was, well, Mace won in the end, so I'd want to have an applause for him for actually correctly guessing, yeah. So what was actually the problem here? So given a set of numbers and some extra number x, what is the largest subset of my set of numbers such that no two elements sum to something larger than x? And the answer is pretty straightforward. At the first glance, you just take every number which is lower or equal to x over 2, but then you maybe have to do something extra because you can add at most one extra number which is larger than x over 2, but which does not sum to something large. Thanks. And you can find all these elements in a single pass. Maybe I should mention one edge case, which failed for a lot of people, was that if you have only items which cost more than x over 2, you can actually take a single item to include in your set. And many people here gave as an answer 0. So that's where most of the wrong answers came from. I guess that's everything about problem A, and Ludo will tell you something about problem B.
Yes, so the next problem was birthday boy. This was the second most solved problem. Still a lot of wrong answers. So the problem was given some dates. What's the biggest gap between the date and the last birthday? Yeah, basically any smart way of counting the number of days after a birthday worked with some DP or but there were some pitfalls. So like at the end of the year you have to begin again, and there were some conversions between months and days and just converting them to integers and back. Yeah, and like -1 for the first day is also not correct. Yeah, and just dates are terrible. Like this. Okay.
All right, so I will explain something about problem F, which is the third most solved problem. You have a bunch of investment opportunities, and the question is which one should you buy so you can retire as soon as possible, and it's given how much money you need to retire. So what's the main observation? You always want to buy an investment opportunity immediately because you can borrow as much money as you want without any interest. And if you plan to retire on day D, you might as well buy every single investment which pays off before day D. So there's two solutions here. You could say I do a binary search on the day on which I retire, and then I buy every single investment which happens before that, which pays off before that. Another solution is for every investment, compute the day on which it starts paying off, and then just greedily take them, and your day of retirement will start decreasing, and you keep buying investments until they stop paying off before the day on which you currently plan to retire. And either of these solutions take O n log n. We got a bunch of quadratic solutions to this. Those don't work. So you do need to sort this list. Next slide, please. So the biggest pitfall here was overflow. Worst case scenario, when you only have a single investment opportunity and it costs 10 to the power 9 and it only pays 1 a day and you need 10 to the power 9 money, you might only retire on 2 times 10 to the power 9 days. On the other hand, if you calculate on day 2 times 10 to the power 9, in the other extreme situation, you might have made 2 times 10 to the power 23 money. And that does fit in any standard integral type in C, C++, or Java. So next slide, please. Actually, the test case which tests for this was only added this morning. And there were 13 submissions which failed only on this test case. So in the last few hours, we really screwed all of you over. And that's it. I'm moving on to C.
Thanks. All right, next slide. So here the problem is, given some volume V, find 3 integers, A, B, and C, that are the height, width, and depth of a cardboard box that multiply to V, such that the total surface area is minimal. So a very simple idea you could do here is iterate over all possible A, all possible B, all possible C, check whether they multiply to V, and then minimize this surface area you see up there. This is too slow, so you can do one optimization. Next slide. You can only check 2 integers. So if you know A and B, you can just check whether V is divisible by the product of A and B. Calculate this number C, and then just do this minimization again. And then this is still too slow, because V is 1 million, I think. So next slide. But you can actually realize that at least two of the numbers a, b, and c must be less than the square root of v, because if two are larger than the square root of v, their product will be at least v, or strictly larger than v, which is bad. So you only have to iterate over pairs a, b less than square root v, and then you can get within the required runtime. And then there's one more idea. You can also calculate a list of all divisors of your number v. It turns out that if v is at most 1 million, there's at most 240 divisors. And then you can run the quadratic solution above or the cubic solution above even, I think. That's about it here. Nope.
So the next problem was game night. So the problem was about organizing letters of A, B, and C together. The solution was basically trying the order ABC or ACB, and then try to position the first A on every possible index. You can't, so you know how many A's, B, and C's are in it, so you know where the A starts and ends, and you count the number of A's in it, and then check how many there are missing. And just naively, it's too slow, but if you do it with a sliding window, you change the index by 1, and then like your circle rotates, so there are only 3 values changing, and those you can count simply, and then it's linear. That's it. And you can also use a prefix sum and then calculate it immediately for a given range. That's also fine. Yeah.
All right, so this problem, we thought it would be much more difficult than it actually was. We'll get to that in the end. So next slide. So the problem is, given 4 integers, find the area or make a quadrilateral with these side lengths and find the maximal area of this quadrilateral. So next slide. It turns out that this area is maximal if the quadrilateral is if the 4 points lie on a circle. And also you can realize that if you change the order of the edges, the maximal area doesn't change, because I can basically change 2 edges, swap them, and then nothing changes. You can draw this out. Sorry. We can quickly prove that a circle is actually optimal. So if we take the picture on the left, where it's already a circle, and then we deform it a bit to get a picture on the right, you can see that this shape has some kind of circumference. And we know that for a given circumference, the circle is the shape that maximizes the area. So now if we move it back into the circle, we know that this is the maximal area you can get. And now we just subtract the red parts, which have constant area, so this also gives the maximal area for the square that's inside. Okay, so now the point is lying on a circle, and from this you might know from mathematics that the angles of 2 opposite corners sum to 180 degrees. So next slide. So from this you can write down a formula for the length of the diagonal. And now you can either solve for this angle alpha and calculate the area, or you can solve for the length of the diagonal f and use Heron's formula for the area of a triangle. Okay, next slide. Then there's a couple of alternative solutions where you don't have to prove that the points have to lie on a circle. So for the first one you can binary search on the radius of the circle. For the second one, you can also ternary search on the length of this diagonal f. And then there's one more solution, surprise. You can use this formula and be done in 2 lines. And we didn't know a lot of people would know this formula because none of us knew it. We found it on Wikipedia, but we didn't think you would know it. But many of you knew it, so you were in luck. Harry.
Right. I think we're now making the transition to certainly the harder problems. And this one was, of course, named after myself. My 2 brain halves don't really work together. Well, what were you given here? You were given some sort of graph with edges, and you started in a node S, and you had to end in a node T. But one of your brain halves wanted to get to T as fast as possible, and the other one wanted to get there as slow as possible. So what I'm going to do here is sort of explain the solution for an acyclic graph, but the same algorithm works exactly for a cyclic graph. So this looks sort of like a minimax type problem. You might do, I don't know, alpha beta pruning, or, well, don't do this, please. It's probably way too slow and it's very hard to implement. What we're actually going to do is not start from S, but start from T. We reverse all edges, and then we're going to do some sort of Dijkstra, which is slightly modified to include the fact that sometimes we want to be as slow as possible. Next slide, please. Okay, so we're going to give every node two states. A red state, which says something about going to T as fast as possible, and a blue state, which says going to T as slow as possible. Basically, whether the left or the right brain half has the choice in a certain node. And initially, I put all the red ones on infinity, meaning that it is guaranteed that with infinite time, you can get from a node to T. At most infinite time. And similarly for the blue ones, that in at least 0 time, you will be able to get from a node to the end. And we're now going to do a Dijkstra process which goes through all these nodes, the red ones and the blue ones. And we can relax a blue node, or the blue part of a node, if you will, if we've relaxed all the red parents, which in the original graph were actually children. And similarly, if there's no blue node to relax, we can relax the red node, which has the smallest distance. So this is actually very similar to a normal Dijkstra idea. And we're going to basically watch how this works for this graph on the left. Next slide, please. Okay, so we can start by relaxing the blue node T. Well, of course, I mean, it doesn't have any parents, which is very sad for this node. And then the red nodes 3 and 4, we can actually update using this information. So if you go to the next slide, please. You will now see that it is guaranteed, if the fast half gets to choose in node 4, that we can reach the end in 5 time units. And similarly, we can reach the end from node 3 in 1 time unit. Next slide, please. So we can now also update the red part of node T, which gives us something about the blue parts of nodes 3 and 4. Next slide, please. So you see this happening here, so nothing special here. And yeah, sure, continue. So now we've done all the parents of node T, so we can now do the blue part of node 3. And basically this says that if you start at node 3, you want to go directly to T if you're the slow half. I mean, there's no other option than doing this. And now that we know that this blue part of 3 is set at 1, we can push this to 4. Next slide, please. Another one. Oh, right. I'm sorry. Never mind. Okay, so now that we're doing the red part of 3, we can push this to the blue part of 4 and see that if you can choose, if the slow part gets to choose in node 4, then you need at least 21 time units to actually get to the end. Okay, so now we've done node T and node 3 completely, and now we have another blue part that we can relax, namely the blue part of 4. Next slide, please. Next slide, please. Yeah, so now we can do the blue part of 4, which then updates the red parts of 1 and S. So now that we've done this, next slide please, we now can do the red part of 1, sorry. You don't want to do the red part of 4 because that one has a higher distance to the end than 1 has. Yeah, 1 has distance 3 and 4 has distance 5. So your normal Dijkstra priority queue will say that you have to start with node 1. And then everything is updated. Then we can do the red part of 4. Afterwards, we can do the blue part of 1, if I'm not mistaken. Yes, okay. And after the blue part of 1, we've basically pushed everything. And continue, please. We can do the blue part of S and then the red part of S. And what you now see is that we've basically, one further, please. We've basically reconstructed the entire decision graph here. So if you start at S, if you're the fast brain half, you want to go to 1. And if you're the slow brain half, you want to go to 4. And this graph tells you completely what happens. So the solution here was a modified Dijkstra, and this is what most of the people who actually solved this problem also did. Yeah, I think that's it.
All right, problem K. So this was, I don't know, was it even solved before the freeze? 2 times. Nice. We expected more solutions here, but let's go through the solution. So given a tree T, we want to find a minimal number of edges we have to add to it so that it becomes biconnected, so that like whatever edge you take away, it will always remain one component. So can we next slide? So one thing that's kind of, I think the first step here is you have to add one edge to every leaf at least. If a leaf doesn't get an edge, you can just remove the leaf and the graph becomes disconnected. So this gives a lower bound of L/2 edges we need to add, because one edge can connect 2 leaves. But we have to be a bit clever with it. So for example, in the graph you see here, connecting nodes 3 and 5 and connecting nodes 4 and 6, this won't work because then we have to connect nodes 1 and 2. And then the edge at the top, if we remove it, there will be one component on the left and one component on the right. So basically what needs to happen, for every edge in our graph, there has to be an edge going from the left component to the right component. And the intuition here is just like, we have to match leaves to other leaves that are far away. Next slide. So one thing we can do a DFS, number the nodes, the leaves in the order we encounter them from 1 to L. And then we just match vertex I with vertex I plus L/2. So you put them in a circle and you match every node leaf to the one on the opposite side of the circle. And it turns out this works. So it's really nice. Next slide. So here's a quick proof. If you pick an edge, you can prove that the indices on the left component and the indices on the right component, they both form an interval on the circle. And then if you take such an interval L and add to every integer in it L/2, then the intersection with the interval on the right is never empty. So there's at least one edge going from the one end of the edge to the other end. So this works. I think, is there more here? Can you, next slide? No. Okay, so one other thing that worked here is you could pick any random pairing up of the vertices, then check if it's biconnected, and if it's not, just try again, and it turns out that you only need 3 or 4 attempts before this works. Yeah, next one.
All right, so we're moving on to the really hard problems, the ones that weren't solved at all before the freeze. So we had some difficult problems this time around. Usually most of the problems get solved before the freeze, but this time there were 3 that were unsolved. So first slide of this, please. So if you'll recall, you have to count entirely unsorted sequences that are a sequence of numbers where none of them is in order individually, where in order individually means that all the numbers before it in the sequence are lower, all the numbers after it in the sequence are higher. Next slide, please. So here's an example of a sorted node. All of the elements before are indeed lower, and all of the elements after are higher or possibly equal, which is also allowed. Yes, next slide. This is an unsorted element of this sequence because there is an element before it which is higher, which is not allowed. Next slide, please. And then the question is, you get a sequence of integers. How many ways can you permute them to make unsorted sequences? The main trick to this problem, as I see it, is to do it in 2 steps. You do the easier case first, where you assume that the inputs are all different. And then you afterwards look at your analysis and you see what do I need to change in case some of these numbers are different, and you'll find out that it's pretty similar. So on the previous slide, so note that we're going to assume that the sequence is sorted. Yeah. In particular, when they're all distinct, we're just going to assume they're 1 to n. So let Pn be the number of these entirely unsorted sequences you can make with 1 to n, and then we're going to do an ordinary dynamic programming trick where we're just going to count pk, assuming that we know p0 to pk minus 1. So the first thing you note, that the thing we're actually going to count is sequences which are partially sorted, so that have at least one sorted element. So you say pk is all possible permutations, k factorial, minus the number of sequences with at least one sorted element. And then you split these on the location of their first sorted element. And now we need to know, what do sequences with their first sorted element at index I look like? They look like this. The value I is at location I. The first I-1 values have to be an entirely unsorted sequence, because otherwise, if there was a sorted element in there, then that would be the first sorted element. And then the last k minus I elements can be any permutation of the remaining k minus I elements. Next slide, please. So how do you split this? The number of sequences with first sorted element as I is pi minus 1 times k minus I factorial. And you could do this computation OK for pk, and that gives a total runtime of O(n) squared, so quadratic, as long as you introduce your immediate results modulo this prime, and also, of course, pre-compute your factorials. All right, next slide, please. What do we have to change in case some of the elements are equal? You can do the analysis and you can find out that actually most of it stays the same. The problem is with these factorials. So these were permutations of distinct integers, and now they will be permutations of possibly equal integers. So you'll know from your combinatorics class that the number of permutations are given by a multinomial. And then the last crucial observation that you need is that these multinomials, although you need to compute quadratically many, and computing them individually would take linear time for cubic time total, because you have these partial multinomials available, you can update them in constant time by only multiplying by a number and dividing by a number. And you need to do all these computations modulo this large prime. So you need to use a modular inverse here. And this is, I think, this slide. Yes? We are missing an opening slide for this.
Thanks. Yes, so this is problem I. You have, okay, there's echo. You had a large road network with a few shelters with a given capacity, and there were people living all over the graph, and then you want to assign everyone to a shelter such that the total time it takes until everyone is at their shelter is minimal. So let's go to the next one. The first observation you make is that if it's possible in time t, then it's also possible in time t plus 1. Because you can just make everyone wait a second, right? The aliens aren't coming soon anyway. So, and then we're asked to find the smallest feasible t. And then whenever you see this, your brain should immediately say, okay, this is binary search. So let's fix a time t and try to solve a decision problem if it's possible in this time. So let's go to the next slide. We can pre-process the graph, compute all the distances, and now for a shelter and a location, we can just check if the distance is smaller than or equal to t, and if so, we can send people from location j to shelter I. This looks like a classical flow problem, so let's go to the next one. So this is what it would look like. We have vertices on the left for the shelters, vertices on the right for the locations, and then the capacities for the shelters are the number of people that can be sheltered. Then right we have the population, and if we can find a flow which is equal to the whole population, then we answer yes, and it's possible to assign people. This will give time limits because the graph is very large, because you have 100,000 shelters. So how are we going to solve this? We can use the structure of the graph because one side of the bipartite graph is really small. It has 10 vertices. So let's go to the next slide. So it turns out there's a lot of equivalent solutions. So in this example, we matched shelter 1 with 3, and then 1 and 2 with the red shelter. So if we go to the next slide, we can also permute them like this, and the next slide, and like this. And so the trick here is to merge together vertices on the right side that have the same neighborhood on the left side. So 1, 2, and 3 have the same 2 shelters as their neighbors. So we turn them into a big vertex with population, the sum of the populations living there. So next slide, that's what it looks like. So now there's only 2 to the power s vertices on the right side, which is only 1,000 or so, and this will pass. And the homework exercise, you can do this without flow, but with Hall's marriage theorem. But we won't go into that here. And the last problem, D, let's go to the next slide. So you are given a finite state automaton with label L outgoing, label R outgoing, and the vertices were colored, and you were asked to find a word that distinguishes 2 initial states. So here, following R from A and B gives you 1 for both, so that doesn't help. But on the right, you see that LR is a distinguishing word. So how would you solve this? Let's see. So the first solution you think of is breadth first search, right? So you have a state, A comma B, saying one person is in A, one person is in B. And then while there's something on the queue, we take it off the queue. If it's the answer, great. Otherwise, we go left, we go right, we push that on the queue. And we just continue doing that. So this will give time limit. So consider this graph. R moves the B forward and keeps A in place. L moves A forward, keeps B in place. So this will have a quadratic number of states, and this will go wrong. So how can we solve this? Well, you can think about if you really have to visit all states, right? So if we magically knew that A and B could not be distinguished and B and C could not be distinguished, then we can conclude that A and C cannot be distinguished. Next slide. Because if there's some path distinguishing them, excuse me, and you follow that from B, then because A and B are indistinguishable and B and C are indistinguishable, you want it to have the same color as A and the same as C, but those have different colors by assumption, so this is a contradiction. So if we go to the next slide. So A and C must be indistinguishable as well. So how can we use this? Let's go to the next one. So what is the problem here is that we don't a priori know that A and B are indistinguishable, because that might require exploring the whole graph. So here comes the magic trick. Next slide. We just pretend that they're indistinguishable, right? So if we have A and B comma C coming into our queue, we just pretend they're indistinguishable and discard A comma C. Why does this work? Well, either we were right, that's great, we correctly discarded A comma C, or we're wrong, but then one of A comma B and B comma C must also be distinguishable, right? If there's a path from A that gives you white, C that gives you black, then following that path from B will distinguish B from one of A and C. So we will still get the correct answer. So how do we implement this? We just use union find, and then we mark, if A comma B comes through our queue, we mark them as indistinguishable, and that's our union fight. And then we just continue as normal. So next slide. Why does this work? So if we discard A, B because they're in the same set, then we have this sequence of tuples that already passed through our queue that were already expanded. And so if A, B are distinguishable, then so is one of the other pairs. And we don't have to consider A, B. So you can do this with a union find data structure in n alpha n time with alpha the inverse Ackermann function. And you actually get that this is the shortest path by construction because it's a breadth first search. And that's the answer. Oh, and the answer is usually quite small, and at most n-1 as a corollary. Yes. Here we have some statistics that I didn't read beforehand. So commits, okay, great. I think we should probably move on because time is brief. One thing I quickly want to mention is if this is your last year competing, we're always looking for new jury members, so please talk to one of us if you're interested next year. What else do we have? Do we have more slides? That's it? Okay, let's move on then.
Okay, so we are setting up the presentation of the results. Apparently I have to entertain you for 2 minutes while this is happening. I will use this time to make some announcement. Regarding the food, please, so there will be a food truck outside. Have only 1 burger for each person, but you can have as many fries as you want. And the portion should be enough for everyone, so you should be full after having the burger and the fries normally. Another thing, I would like to thank again all our volunteers that put a full day of work for organizing this contest. So applaud them, please. And also our jury members, which worked a lot. Our sponsors for giving us the funds to. And finally, all of you coming all the way from Netherlands. And I hope you enjoyed this first edition of the BAPC in Belgium, and we hope to host you again in Belgium in the next coming years. By looking at Guillaume, I see I still need some time, or okay. So,
oh, where is my clip? It's okay. Okay, so the screen will glitch for 5 seconds, promise. Okay, so first thing first, we will begin with the companies. So we had a lot of companies sponsoring the contest and participating at the same time. And so they participate on site with us in another room. And so some of them won prize. Okay? So we had actually 12 teams. Yeah. And so we had Booking, Ortec, IMC, Quintic, SIU, Ortec, and Better Be. Okay. And so we will do the usual. So you know it works mostly. We have things that were already known before the freezing, before the freeze of the scoreboard, and you have yellow entries that were submitted after the freeze. Okay? And so usually we do something like I press on space, everything go up, and each time it selects a yellow entry, and then you are going something like oh, okay? And then you do either way or okay? As usual, you know the music, okay? So here are the problem totals for all teams, for all company teams. And so so Butterby is 12th. EMC, yay! Yay! And so Ortec is 7, Ortec 2. Yay! Quintec is 6th. Booking 2 is 5th. Sorry. EMC 1 is 4th. In 3rd place, Ortec 1, congratulations! So, sadly, we only have medals for the first team. Oh, yeah, I know. But they are nice. They are nice, they are a bit rectangular. Okay, so in fact, we already know the final top 3, okay? Because Sue is obviously second. So congratulations. But the main point is to know whether booking solved the last 2 problems, okay? So let's go for drum rolls, please. Yay! Yay! So first team is Booking 1. Congratulations. François, please. No, you can give it with me. Okay. So I have actually 3 medals, of course. So congratulations.
Thank you.
Congratulations. And congratulations. Oh, sorry. Squeeze. Okay. So that was for the companies, but of course, most of you are interested in the main contest. Okay? So I will take like 5 seconds to. Yeah, there are a lot of things on the screen. Okay, so it will take some time as we have already 160 waiting submissions. Okay, and so this is the scoreboard at the moment of the freeze, at the time of the freeze, okay? And so we have all these things to review. Okay, and actually we already know the 34th team. And let's go for it at UC from here. And then we go. Yeah, oh. Yay! So 44th Full Metal Algo from UC Louvain. Philippe Senko, 43rd. 42nd Null. Yay! Yay! So Sudo Q from Leiden. Yay! Yay! No, the Musselman is 41st. Sorry. So Treaty is 40th. Sudoku, again, another successful submission. The Eckermans is 39th. Yeah. Turkars, yay, congratulations. And Game of Threads from UC Louvain, 38. So Sudoku, 30 seconds. Okay, do not blame me if I don't read this one. So double whiskey PP, 31st. 30th, Extreme Pythons V2 Alpha pre-release. Are the boys back? Maybe. Yeah, the boys are back. Quantum Bogosot. Yeah, 29th RO1. 28 set winners through. Better hits than needs. 27th. PB something. 26th. Oh. Yeah. And D1 25th. Quantum Bogosot to 24th. The boys are back 23, 23rd. Happy birthday, Lo, 20 seconds. Yeah. Googling Stack Overflow is maybe 21st. Immutable is 20th. Correct the record. Yeah, congratulations. I do not want to read this one. So Team Ne. Then Trivial is 18th. 17th for Kökentafelwiskundingen. Yay. Calculating maybe? No, not for this one. Not for this one either. Enter the functors Hungry Turquoise Facebook blockchain is 13th. 12th to correct the record. 11th Prometheus. Team Cap is 10th. And everything stopped there, because from now on it will be manual clicking on the spacebar. Okay, so Team Cup is 10. Congratulations. It is the same as previous. We have only medals for the first 3 teams. Okay, so I will call them when the moment has come. Okay. Oh, and so Snack Overflow is 9. Congratulations. Okay, I'm sorry. I'm sorry for the duck. We took a lot of time to place the duck everywhere, but not on there. Congratulations. On the hook. Oh. Oh. So on the hook, 7. Congratulations. Pokémons from Mons are 6. Congratulations. Yay! Yay! It never stops. So Quantum Bogosort from Université Libre de Bruxelles are 5th. Congratulations. I think, since we are the 5th place, you can always get up and show yourselves. Where are you? Yeah, congratulations! Q++? So Team Rationals ++ is 4th. Ah yeah, they are gone. They are gone, they have to take the train, they warned me. And now we are going for the medals. And the question is, do mostly Harlem Bogosort solve the last problem or not? Because if they did, they are first, for now. Oh! And so the 3rd team is CPU Mons from University of Mons. Congratulations, please come. Yeah, please, we have medals for the 3 members of the teams and 2 coaches. So take your coaches with you. Where is your coach? Okay, so no coach remaining, no problem. So here is the one for your coach. Okay.
I'm a coach. I'm a coach. Yes,
Say, it's okay, congratulations.
Thank you.
Congratulations. Oops. Excuse me. Congratulations. Hop. Finally. Sorry. Up. Blue, blue, blue. Congratulations. And so here is. Okay, should be okay for the photo.
The other one, we need go. We take to give it to. Enfin, je vais la donner à.
Okay, just press on space bar. Space bar. Okay, and so the 2nd team is. Okay. And so the 2nd team is the Tyro Coders. I don't know if I pronounce it well. So, congratulations. No coach? Okay, no coach. Do you have a coach? Do you have one? No, no coach at all. Okay. Hop. Sorry. Congratulations. Sorry. Up. Congratulations.
Thank you.
Congratulations, and Iris, your prize. Yeah. And finally, the first place, and you already know them, of course, but the first place, and it's my greatest pleasure to announce it, because I'm the coach with François. And so I will really happy to give myself a medal. Oh, it's broken. No. Okay, it's mostly harmless bogus notes. So, congratulations.
Thank you very much. Thank you.
Congratulations. Hop. Congrats. And then, oh yeah, thank you.
Congratulations.
Thank you. Woo! So, that's the end. It's done. And what is left is the most interesting, in fact. It's the dinner. And wait. Too early. Wait. We have something to say, like only one burger per person. Sorry. And that's all, I think, François. François? That's all to say, one burger per person?
Yeah, but you peux avoir des frites, plus de frites.
But you can have any amount of fries that you want. Okay? So see you at the dinner. Oh yeah, we have additional keyboards here.
Can I just get a huge applause for the organizers, please? That doesn't work. Applause for the organizers! Woo!
And so, keyboards. So ULB, I know them. And that's all.